So word got around that I was visiting AMD Austin and ran into these guys. You wanna introduce yourselves?
Sure, I'll go first. I'm John Grimm. I'm the Director of Engineering for Linux Kernel and Virtualization Development, and this is...
I'm Tom Lindacki, and I do a lot of kernel work involving encrypted virtualization, and that's the main focus right now.
We're all about those kinds of things in level one and in our audience, and so I was just like, okay, I have to use this opportunity. What are you guys excited for? Threadripper is launching. We're at 96 cores on the desktop. There's high-end desktop. There's Threadripper Pro, and bringing that up and enabling that. There's going to be some kernel patches. You can't just throw more cores at the kernel. There needs to be some optimizations there. So, what does that look like?
Sure. So my team, just to describe where we sit and what we do. My team is primarily Austin, 1/3 of us, and probably 1/3 of us in Bangalore, and 1/3 of us other places in the world. So Europe, Germany, Australia, wherever I can find the right kernel developers to work for us. So one of the teams that I've been able to enable and build over the last 2 to 3 years is actually a scheduler memory management team. So as you called out, high core counts bring new challenges. And they're very focused on doing measurements with the Linux kernel, understanding where maybe the brittle points in the Linux kernel are related to scalability. Maybe there's some locking issues where you find that contention, etc. So we're really excited to actually have a team focused on that. So, definitely on the scheduler side of things, but then we have technologies also, definitely on the virtualization side of things to sort of improve performance and scalability as well. IOMU technologies.
They know me.
All right.
I'm known. This is not good.
That. Well, my reputation for IOMMU advocacy precedes me. I just want to be able to run virtual machines with GPUs the way that virtual machines run with CPUs for like a decade now. Come on.
I've heard that. Just improve virtualization overall and the performance, less overhead, add security to it. Lots of fun features there for us as well.
Yeah.
I know you heard a little bit earlier today about SEV and SMP and confidential computing.
I wanted in client so bad.
Okay, so SEV, it's so simple in retrospect, but it's complicated to implement, but it's secure encrypted virtualization. What this is you run a bunch of virtual machines, you have slots in memory to be able to handle it, but the memory controller on the CPU is what handles the encryption and decryption of the regions of memory. But it also turns out that when you're running processes inside of all of the different virtual machines, it's also handy sometimes to have nested page tables that are also encrypted. And so you can have secure nested pages as well. What that effectively means is hardware accelerated encrypted virtual memory. No performance penalty, in other words.
So it's based on a hardware virtual machine. And the way that that's traditionally associated is there would be like a customer VM in the cloud. Of course, there are projects out there that use hardware virtualization in other ways. So for instance, the Kata container project, which supports SEV now, can run a container as a hardware VM. And so that way you get a unique encryption key for your container, which you can just run with standard container tools. So there are a number of ways that you can use the virtualization, but at the hardware level, it is based on what we would consider a hardware virtual machine. I will mention just on the encryption keys, so on Rome and Milan, we did support up to 509 encrypted VMs. In our most recent 4th generation EPIC, that's the codename Genoa part, we support 1,006. So that's gone up almost double.
It's been an ongoing
debate.
No, just an ongoing piece of work, right? Starting when the first server part came out that supported it, we worked with memory encryption in the host first, moving to the guest, right? And that's the SEV. And now we're into the next phase with secure nested paging and preventing the hypervisor from even messing, even though it can't write specific things into memory on an SEV guest, now with SMP you prevent them from writing into that memory completely.
You were asking about other areas that my team really focuses on. Let's say calling out besides scheduler, memory manager, things like that. We do focus on a lot of our IP, the hardware features that we develop. Are there areas that are important for EPIC, so the enterprise and data center area? RAS is one of those areas, right? Machine check architecture, reporting errors up from hardware to the OS, to an administrator, finding out a failing a component or a protocol so that can be serviced is critically important for a data center. Got to keep it running. So my team spends a lot of time working on the MCA subsystem as well as EDAC and error reporting, things like that. So that's
EDAC for the kernel.
Yes.
Just barely happened.
yeah. Error detection and correction. I guess I should spell out what EDAC is.
So why is the EDAC stuff important? Well, your hardware abstractions only take you so far. There has to be a signaling mechanism from the hardware abstractions up to at least the kernel layer to let the kernel know, hey, I'm dealing with a hardware issue here. It shouldn't affect any of your running processes. Like we've recovered, we've corrected a memory error, or we've dealt with a bus error or whatever. Okay, well, EDAC is more on the memory side, but you want to have all of that plumbing in place, and you want to make sure that it is very polished, very solid, very reliable code so that you can really count on those subsystems. And a lot of the time, especially when we're talking about a new DDR5 platform, some of the I's have not necessarily been dotted and the T's have not necessarily been crossed in the Linux kernel, because you don't want to give away what you're doing, so you don't want to, because not everybody has access to the hardware while you're bringing it up. Now the DDR5 is launched, it's not really an issue, but this is why sometimes like, okay, I want day one availability, and it's like, well, we had to coordinate with a lot of people, and a lot of the people we needed to coordinate with didn't physically have access to it because the DDR5 memory hasn't been produced yet. But less of an issue today, but I can understand 6 months, a year ago, maybe a little bit of a challenge.
In this case, I have a system with Ubuntu OS, and then I'm gonna inject some DRAM ECC correctable errors. So in this case, these errors are not like fatal for the system, so the system should keep running, and then we should have enough information in our D message, in this case, about the error that happened in the system. So I'm gonna inject DRAM ECC using the ING, and then I'm gonna, here I just need to specify the address where I want the error to be injected, and then I'm gonna tell inject a correctable error. So this internally is gonna be performing error injections in that particular address. So the system is gonna be notified about this error, and then it's gonna be reported to the machine check architecture that we have, and then we're gonna get the error in the D message.
Yeah.
So
the lines with brackets are actually from the Linux kernel itself.
Exactly.
Yeah.
Yep. So in this case, I'm gonna grab my D message. So there are a lot of information. So I'm gonna just grab for hardware, because it was like a hardware error. Oops. My bad. D message or grab hardware. Okay. So this is the error information. So here in the top we have machine check event log, and then there is a hardware error. In this case, it is a corrected error. So we inject a correctable error, so it is the error was corrected. And then no action required, right? So from system level perspective, no action required. We were able to contain the error. Everything is doing great.
And that's the plumbing that AMD is providing with, as you're slowly taking over, or quickly taking over this server universe, it's like, oh, this is a nice quality of life enhancement.
Yeah.
And so it's like your software engineering teams are bringing this low-level visibility at like the bare metal level up into the kernel where administrators can see it, and more importantly, take action on it.
Yeah, exactly. Yep. And actually, for this demo, as I mentioned, we can modify the fruit text, right? So I made a small script that modifies the fruit text of this platform, and actually the demo one. So I'm setting the fruit text to level 1 text.
Nice.
Nice. So I'm gonna change my fruit text. Oops. Sorry, my bad. Right. So in that case, I modify my fruit text. Then I'm gonna be injecting the error again. So now in the D message, we should see like 2 errors, right? The previous error and the new error. And this new error is gonna come from the fruit text.
They put way too much effort into this demo. Way too much effort.
Yeah. So I'm gonna do again the message script hardware.
Hey, yeah, look at the new error.
Yep.
Look at that.
So this is the first error that we already have in the system, the one that we injected. So before, the fruit text was locator P0MD1, and then when I changed the fruit text, I put level 1 text, right? So now we know that there is a faulty DIMM, and then probably the owner is level 1 techs.
Excellent, as it should be.
Yep. One has been very excited about this demo.
Well, the other thing that's happening here is we're injecting an error and the machine isn't rebooting. There's no, it's not a catastrophic error. The kernel is saying, well, this error occurred and it was non-fatal. We can continue on, which is great. But what happens when it's fatal?
In this case, when the system is not able to correct the error, it's a non-correctable fatal error. So the system is needs to notify the different devices inside the CPU that there was an error, like, hey, we should stop. We should not continue doing execution. Something is going wrong. So we send something called sync flood to all the system, and then later, if it is set in the BIOS, we send a reset, right? Because something was wrong, we need to send a reset to put the system back online, right? And now I'm gonna do that experiment. So I'm gonna inject an error in the same address, but this time this error is gonna be uncorrectable. And as the system has poison disabled, the system should send a reboot, and then we should get it back in a few minutes or seconds.
So keep in mind, if this were a system running a bunch of VMs or containers, as I was saying before, we're injecting a single bit error here, and it just, we rolled a 1, and now the error was in kernel space, or it was in critical error for some device driver or something. It was something that was not recoverable at a machine level, but it's not going to be recoverable from the kernel level. You get a reboot.
So that's one focus. Another area that we're deeply invested in right now is CXL. I'm assuming you've seen some CXL.
So maybe
today.
just a little bit.
Okay,
Yeah.
okay. I don't know if anybody's talked to you about SDXI
Not yet.
or TMPM.
Nope.
All right, I get to be the first one.
Yeah.
That's good.
Walk us through SDXI and TMPM.
Yeah.
What is it?
So two different, I'll call them data movement technologies, DMA engines, if anything else. Sort of focused a little bit different. So SDXI is a standard in SNIA, so it's co-authored between VMware, AMD, and Dell to be a standard. So anybody can go implement this, and AMD, we're obviously going to work on that standard and help bring it to market with hardware. The idea of being able to offload things like memory copies, what we'll definitely start with, and accelerate that rather than using our cores. We have lots of cores, but there are some people that really want to use those cores for other things besides moving memory. One thing that I've loved at AMD since the day I came in was an attention to talking to our customers and said, what are your pain points? Not only what are your pain points that you have right now, but also say when we come out with one generation to the next generation, we go back and ask those customers, okay, let's just pick Rome. We'll talk to the customers that had Rome and what worked well, what didn't, what would you like to see in there? I'll call out a great customer of mine I consider as Google's kernel developers. We've been working very closely on SEV, SMP. I love them because they're willing to collaborate on it. They give engineering resources, we give engineering resources, figure out how to work things together. They'll review our patches, they'll come up with patches of their own. I love customers like that want to collaborate out in the open as well.
It's a double-edged sword with Linux, the cooperative nature of it. There's a lot of commercial companies pouring a lot of time into developing for Linux, but at the same time, there's a lot of people that are doing this because it is day job adjacent. It's like Linux makes their day job a little easier, but their day job is not tasking them with specific things that they have to accomplish in the Linux kernel. It's just our mission is to use the Linux kernel to do our business over here. And yeah, it would be nice if we added support for DDR5 or AMD's thing or whatever. That's not necessarily the mission of the people that are doing that. Now, AMD is employing more and more people to work on the Linux kernel, and some very famous Linux kernel hackers that I was able to meet during my time at AMD. But ultimately, it's not like Linux is from some company like Microsoft. You can't just call it Microsoft and be like, hey, I get a scheduler issue. We need to, put our heads together and work on the scheduler issue. And it's like, well, actually, wait a minute. That probably worked out better on the Linux side than the Windows side. That might not be the best example.
So the fun part is, Tom was in my team before I came into AMD about 6 years ago. And at the time, the team was maybe 8 kernel developers total.
Well, that's not going to work if you're going to take over
Yes.
the server universe.
Yes. But, you got to start where you got to start. And Naples was the beginning of that journey, obviously. What's been fun is seeing that, not only the technology take off, and the customers love it. but also being able to, because of the customer growth and demand, is being able to grow my team to work on a lot of different things we couldn't. So that's been a lot of fun to really grow that team to, have subject matter expertise in various areas, a team dedicated to looking at, scheduler changes, either proposing them or reviewing them, seeing how they actually work and make sure they don't regress anything on Epic and make improvements as well. So that's been pretty tremendous to go from a team that was around 8 or 9 engineers, primarily just focused internally on making the hardware work, to a team that can look outside and making improvements in Linux in a bunch of areas that aren't always just hardware specific like a device driver, but scalability and performance issues as well.
From my perspective, it looks like the work that you've been doing has enabled a lot of providers to move from high density 2-socket systems into even single socket systems with more chassis. Like the total core count doesn't really change, but they're spreading their workload across more physical chassis. Sometimes the physical chassis are smaller. It's like, oh, we'll put 4 nodes in a 2U or whatever. But the individual machines end up being single socket, and I think that's in no small part as a result of the work and optimizations and that sort of thing that AMD's been doing around their platform. Have you seen the same, or have you noticed any trends like that? Or
yeah, I think that's going to definitely be customer specific and their workload specific.
Yeah.
Right? I mean, definitely people, let's be
more
honest.
and more stuff can be done in a socket.
Yeah, 2P designs are more complicated. There's more things to think about when you have to deal with the communication, the challenges of that, and the latencies, etc. So, if you can put all of that in one socket, that brings down the cost, and that just becomes more compelling for some of those customers. But it's really going to be a customer per customer. There's other people that's like, no, I want that full expansion out there.
Well,
I want everything.
The software is a lot more complicated too, because you still have 2 96-core CPUs. It's just in 2 chassis versus the one.
Sometimes the customers don't even know what they need, and so that's flexibility for AMD. And flexibility is, hey, we're going to just give you a bunch of cores and some really high-speed bus stuff, and the bus can be PCI Express, it can be SATA. That's some of the kind of flexibility that's been implemented in the hardware. So, AMD doesn't assume that they know everything about everything. Instead, they work with customers who are doing business. It's like, hey, our people think you could probably do this, and this would work really well with what you've got going on over here. And then so it's a beautiful potpourri of collaboration. I think seems to work well for AMD from what I gather talking to everybody inside AMD and looking at the product stack.
Tom and I have worked in Linux for a long time.
Nice.
We're the old guys in the team. Sorry to drag you into that, Tom.
The gray beards, yes.
I am probably the oldest.
But because of that, we really do come from a mentality of community and upstream first, right? It's not our way or no way. And we know that we have to help our customers the best. It means getting our code accepted by the upstream community and interacting and collaborating, not trying to force things, but really just treat that as a collaborative playground, if anything else, and get things. And in some places that means heavily collaborating with competitors. People would think, oh, you guys are enemies out on the mailing list, and it's like, no,
we're
not
just
at
trying
all.
to solve the computer science problem.
Yep.
Well, I'd heard about an interesting bug with the C6 resume, and something that dated from something that was added to the kernel in the bulldozer days, coming back to haunt Milan and Genoa. Can you tell us a little bit about that?
Yeah, that was an interesting one to run into. There had been a workaround for some buggy code, like you said, 20 years or so ago, and there was an extra read that actually occurred that would work around the issue. With the high core counts that we were getting to, and we probably didn't realize this for many generations even, it probably wasn't until Milan and Genoa that we identified this as really causing issues on multiple fronts. Multiple people, customers sort of chasing down problems, etc. The problem exhibiting itself in different ways. But just this tiny little read.
It's like, oh, it's got to wake up. I have to read this. And it's like, well, no, you don't on non-broken hardware.
Yeah. And it's like when you got that many cores coming out of sleep, that just added to a major problem. So just seeing that cascade and what that little one line of code pain was causing, and probably causing problems that we hadn't seen for a couple of years even, was pretty amazing to find.
So the other thing, and if you follow my videos, you know this, but it has blown me away, because 10 years ago I was showing how to create a virtual machine and pass through PCIe hardware. And from that, this crazy, like Alex Williamson has done a bunch of work on this, like he's really on the kernel side, has done a lot of this. and there is a substantial community of users out there who want to try to segregate what they're doing for gaming and entertainment and that sort of thing. And the way that they do it is they create a virtual machine and then they pass through a GPU. So they'll build a high-end Threadripper system, or Epic in some cases, and they'll have their GPU for the host operating system, and then they'll pass through another GPU for their guest operating system. And so, like, okay, there's Denuvo and DRM, and Microsoft's got, doing their thing, and EA's got their thing that's monitoring my browsing habits. That's a plug-in thing. And so these game companies, they just can't help but, try to find new and interesting ways to monetize their game launchers. And so it's just like, all right, I'm not gonna play that game. I'm just gonna do it in a virtual machine. And that sounds like a fringe use case, and it certainly was 10 years ago, but now like the Reddit community for that is 700,000 subscribers, and our community is 100,000 people. And not everybody, like, it's hard because there's not super consistent support, but these are a lot of enterprise features that come to or just happen to survive on the client.
I mean, you make a good point also from the standpoint of like maybe these have been sort of fringe or desktop sort of and gaming sort of focused things. But I will say, we've got this investment on the IOU technology where we'll continue to make that better, that the client team just gets to inherit, hopefully, and just means some testing, et cetera, on the platform side. But I'll also say that'll become more important on the data center side, because you're going to have people doing MI, machine learning sort of pass through of GPU devices as well.
Yeah.
And these will be massive devices with tons of SROV virtual functions to be able to pass in.
In a general sense, just look at like in the beginning when we went multi-core, when like 2 and 4 cores on a CPU was a thing. It's like, oh, virtualization. It showed up immediately.
Yeah.
But like for a GPU, it's like I have a GPU and I would like to run virtualized workloads to where I could share 2 operating systems with 1 GPU. And it's like, well, that hasn't happened. And it's like, I don't see the difference in that.
Yeah.
Like,
Well, it will happen. Like I said, the data center use cases will drive that down.
Yeah.
So it will improve on that side.
Yeah, so I'm always surprised. It's like, well, I don't know. We do have that. Intel did GBTG as their approach, but they're abandoning that. Their Flex stuff is SRIOV. NVIDIA has SRIOV, but NVIDIA also lets you do CUDA, so you don't have to do full virtualization. You can do just kind of a lightweight, and if you have a CUDA job, you can share a CUDA job among a bunch of machines. Okay. That runs over OmniPath and InfiniBand too. So that's like it's like if we're talking about virtualization as like, ring 1 virtualization versus container, it's like I don't know. Don't listen to me. But it's really, should be on your radar probably.
Yeah, oh definitely.
And that's the thing that I love about the Linux community and open source, is being able to put this together. It's like, I want to run VFIO, I want IOMMU, I want secure encrypted virtualization for my browser even. I want to run my web browser in a secure encrypted container so that it's harder for things to break out of it. This really is our computing future. And a lot of these technologies that are server only today, they will make their way into regular desktop machines. Heck, they should be making their way into our phones. Our phone hardware, we really should be running apps in phones in secure sandboxes because of all of the history of security issues with all the different apps and everything else in phones. And this is the technology to do that. It just has to make its way down to phones. And I love that the Linux kernel exposes that and makes it easy to get at, and also makes it a little easier to understand what's going on. I'm Wendell, this is Level 1. This has been a very rare peek behind the curtain at AMD. Huge thanks to everybody that I met at AMD. The lab guys, the Linux guys, the RAS guys, everything. It's been just super, super, super amazing. All right, this is Level 1. I'm Wendell, and signing out. You can find me in the Level 1 forums.